In the last class, we have seen the Riemannian curvature tensor. The Riemann curvature tensor in its mixed form can be written as R mu nu lambda sigma is equal to partial derivative of Christoffel symbol with respect to x lambda minus partial derivative of mu lambda mu with respect to x sigma plus Christoffel symbol rho mu sigma mu rho lambda minus rho lambda nu and mu rho sigma. So this is the Riemann tensor. Or the Riemann curvature tensor. From this curvature tensor, we can construct another tensor of rank 2 by the operation called as contraction. Okay. So at a glance, there appear to be more than one possibilities of doing the contraction. But if you see, you can contract mu with nu, lambda, sigma, right? But if you closely look at it, then we can find that there is only one independent result that you can obtain. Whatever contraction you do, you get only one way of doing it. Okay. So I'll write apply the contraction. That is lambda equal to mu. Then I'll get R mu nu, then again mu sigma. So instead of lambda, I'll write mu. That will be equal to mu nu sigma with respect to x mu minus Christoffel symbol mu mu nu with respect to x sigma plus rho nu sigma mu rho mu minus rho mu nu Christoffel symbol mu rho sigma. Okay, so I have done the contraction. Now if you see, in all the terms, mu is a dummy index, it's summed over. Mu, right? Here also mu. So mu is summed over. It's a dummy index. Therefore, I can write R nu sigma is equal to mu nu sigma with respect to mu plus Christoffel symbol rho nu sigma mu rho mu rho mu nu Christoffel symbol mu rho sigma. So this is called as the Ricci tensor. So from the curvature tensor, we can construct a tensor of rank 2 called as Ricci tensor by an operation called contraction. Right? From the Riemannian curvature tensor, we can obtain the Ricci tensor by an operation called as contraction. Right. Now we'll see whether Ricci tensor is symmetric or antisymmetric. For that, I have to interchange nu and sigma. Right, so here I have r nu sigma. Next I'll write r sigma nu is equal to sigma nu with respect to x mu minus mu nu sigma with respect to x mu plus Christoffel symbol rho sigma nu mu rho nu minus rho mu sigma mu rho nu. So this is nothing but r nu sigma. Therefore, the Ricci tensor is symmetric because r sigma nu is equal to r nu sigma. Therefore, the Ricci tensor is symmetric. So next I need an invariant or an invariant quantity that can quantify the curvature. That is something called as a scalar curvature. Okay, so for that I have to now again multiply this Ricci tensor with the fundamental metric tensor. So I get g nu sigma. I am going to multiply the Ricci tensor r nu sigma with the fundamental metric tensor g nu sigma, right? So I will get r sigma sigma, which is a scalar quantity because this will be r11 plus r22 plus r33, sorry, r00 also there, right? So this will be a scalar quantity. So let's represent it by r. Okay, so if I multiply the Ricci tensor with the fundamental metric tensor, then I will get the curvature invariant or the scalar curvature. Or another name is the Ricci scalar. So this is a invariant quantity or a scalar quantity. In Euclidean geometry, r will be 0 because there will not be any curvature. So in Euclidean geometry, r is equal to 0 everywhere. Okay, so thus this scalar curvature will give you a criteria to distinguish between whether a given space-time is curved or not. Also, r can take negative value or positive value. If r is equal to 0, it means there is no curvature. Otherwise, if r has some value, it can be negative or positive, which means the associated curvature will be negative or positive. So if r is negative, the space will be negatively curved. If r is positive, then the given space will be positively curved. If r equal to 0, then it is a flat space or there is no curvature. So that is the importance of Ricci scalar. So Ricci scalar will tell you not only whether it is curved or not, but also whether it is positively curved or negatively curved. So next we will go to Einstein tensor. In the absence of all the forces, if you have a free particle, then the motion of that particle can be described by a straight line. But if you have some forces, then it can deviate the trajectory of the particle, and it can have a deviation from a straight line. It may not be a straight line, right? So in the absence of all the forces, a free particle can have a straight line motion, otherwise not. So any deviation from a straight line motion will mean that there is a presence of force or a field. And there is one more thing, since we cannot remove gravity completely and globally, you can only remove it locally in some point of space, but not globally. Therefore, any given particle will always feel the presence of the gravitation, and it will definitely take a curved path. Or in other words, I can say that the gravitational field can be described in terms of the curvature of space-time. Okay, so this can be characterized by the Riemannian metric. The gravitational field can be described in terms of the curvature of space-time, and this can be characterized by the Riemannian metric or the Riemannian space-time, which is given by ds square is equal to g mu nu dx mu dx nu, where this g mu nu are functions of space and time, and they determine the complete nature of the gravitational field. So this will tell the complete nature of gravitational field. And in one of the classes we have seen that it will give the gravitational potential, right? G mu nu is nothing but it is a gravitational potential. Now the question is how to determine G mu nu, the fundamental metric tensor. Now before answering this question, let's ask what is the cause for this gravitation. So you can say that there is a gravitational field, but what is the cause for this gravitation? So the answer is very simple. It's due to the distribution of mass points. So if you have an electric field, you say that it's due to the distribution of electric charges. Similarly, if you have a gravitational field, then it is due to the distribution of mass points. So distribution of mass points. Or in other words, I can say it is due to the distribution of mass energy in space-time, right? I'll say mass energy because mass can be converted into energy and vice versa. Therefore, it's due to the distribution of mass energy in the space-time. Now, if the gravitational field is determined by the geometrical properties of the space-time, then the distribution of mass energy should also follow the space-time, right? So here we say that gravitational field is determined by the space-time geometry. So similarly, this mass energy distribution should also follow the space-time. Or in other words, I should say that we should be able to deduce the geometry from distribution of mass energy. So here I can say that geometry is dependent upon the gravitational field. Similarly, the geometry should also depend upon the mass energy distribution. Okay. Okay. Now, so what are the fundamental parameters of the gravitational field? So how can I relate this mass energy to the space-time? So for that we use a quantity which is known as energy momentum tensor. Okay, so Einstein actually conjectured that the energy momentum tensor should act as a source of the gravitational field. The energy momentum tensor Okay, so I write the energy, I can represent the energy momentum tensor by T mu nu. Okay, so this is energy momentum tensor, and this will represent the mass energy distribution, and it will act as a source for the gravitational field. So energy momentum tensor will give the distribution of mass energy, as well as it will act as the source for gravitational field. Now the energy momentum tensor is denoted by T mu nu, and it should also satisfy the conservation of energy as well as momentum, right? So we know that energy and momentum are conserved. Therefore, T mu nu must also satisfy the conservation of energy as well as momentum. So in the covariant language, I can write this corresponding conservation law as the covariant derivative of T mu nu is equal to 0. So this is the conservation of the equation for conservation of energy and momentum. And we also assume that this tensor T mu nu is symmetric with respect to its indices. Okay, so therefore in 4 dimension there will be 10 independent components, and this additional property will lead to the number of independent components will be reduced to 6. Now, if these are the properties of energy momentum tensor, then we can ask, is there any other tensor with the same properties, that is conservation law, so that we can equate this with the curvature properties of a tensor. Okay, so I have to connect the energy momentum tensor with the geometry, right, or the geometry of the space time. So how do I connect T mu nu, or I need to find some other tensor which has the same properties so that I can equate this energy momentum tensor with the curvature tensor. So one immediate question that I can ask is whether I can equate the Ricci tensor with the energy momentum tensor. But unfortunately, I cannot equate the energy momentum tensor with Ricci tensor, because Ricci tensor is not following the same conservation law as the energy momentum tensor. Therefore, we cannot equate both the equations. Therefore, we have to find a tensor with the same properties as that of the Ricci tensor, as at the same time it should also satisfy the covariant conservation law. So Einstein addressed all these problems with some trial and error method, and he finally arrived at a tensor which is known as the Einstein tensor, okay, which I can equate to the energy momentum tensor. So now I have to follow the same step what Einstein has followed, and I have to find the tensor which I can equate to T mu nu. Okay, so let's start. So we can proceed from the Bianchi identity. So I have to find the Einstein tensor. So our topic was Einstein tensor. To find the Einstein tensor from the Bianchi identity. So let's start with the fully covariant form of the curvature tensor and the Bianchi identity. So in the previous class we have seen the Bianchi identity for fully covariant form of the curvature tensor is given by covariant derivative of R gamma delta sigma lambda plus covariant derivative of R gamma delta alpha sigma plus covariant derivative of R gamma, delta, lambda, alpha is equal to 0. So this is the Bianchi identity for the fully covariant Riemann tensor. Now I will raise the first two indices. Okay, so how do I raise? I have to do the raising operation. For that, multiply with G mu gamma, G beta delta. So I am going to multiply this entire equation with G mu gamma, G beta delta. This is equal to 0. So when these two act on the first one, then I'll get covariant derivative of alpha, I'll write as it is. Then I'll get R. So gamma and gamma is summed over. Delta and delta is summed over. So remaining is R mu beta sigma lambda plus. Now I have to multiply to the next term also, right? Then I will get covariant derivative of R mu beta alpha sigma plus, now to multiply to the last term, right? Then I will get R mu beta lambda alpha. Now this is equal to 0. Next step, I will contract lambda equal to mu and sigma equal to beta. So here I am doing an operation called contraction. Okay, so lambda will be equal to mu and sigma equal to beta. Then I will get R mu beta. Now sigma will be equal to beta, right? So I'll write beta. Then lambda will be equal to mu. So I'll write mu plus lambda will be mu. Then R mu beta alpha, sigma will be beta plus R mu beta, lambda will be mu and alpha as it is. This is equal to 0. Now here I will interchange alpha and beta, and here I will interchange mu and alpha. Okay, then I will get R mu beta, beta mu minus R mu beta, because this is Riemann tensor and it is anti-symmetric, right? So if I interchange, I'll get a negative sign. R mu beta alpha mu is equal to 0. Now if you see here, there is beta, beta, mu, mu. So everything is summed over. Therefore I can write R, right? Then minus beta and beta is summed over. Then I will get R mu alpha, because beta and beta are summed over. Okay. Then here also mu and mu are summed over. So I'll get R beta alpha is equal to 0. Right? Here I have made a small mistake. Sigma is equal to beta. So here this sigma, when it comes here, this has to be beta. Okay. I made a small mistake. I'm just changing it. So here it will be beta. Okay. Now if you see here, mu and mu summed over, beta and beta summed over. So mu and beta are dummy indices here. So I can always change a dummy index. So instead of beta, I can write mu because it is a dummy index. Therefore, the equation becomes mu r mu alpha minus, instead of beta, I can write mu because it is a dummy index. So these two quantities are the same. So I can add minus 2 times r mu alpha is equal to 0. Or I can take to the other side and write, this is minus, so I can write r plus r mu alpha. This is a positive quantity, so when this goes to the other side, I can write minus r, right? And this 2 I can divide with 2, the entire equation I can divide by 2. Therefore, I will get a 1 by 2 here is equal to 0. Now I am going to multiply with unity here. Okay, multiply with unity. So it's not going to change this equation. If I multiply with unity, it will not change the equation. So here I am going to multiply with the unity Christoffel symbol. Sorry, Kronecker tensor. Unity is Kronecker tensor. So multiplying with unity will not change the equation. Right? So when I multiply with the Kronecker tensor, this will be mu. So mu, then you will get alpha, right? Mu alpha. So these two are summed over and you will get the covariant derivative with respect to alpha, and that is sitting here, right? Okay. So multiplying by unity will not change the equation. Now I can take the covariant derivative common. So that will be r mu alpha minus 1 by 2 Kronecker tensor r is equal to 0. Now entire equation I am going to multiply or erase with g nu alpha. So g nu alpha minus half g nu alpha mu alpha r is equal to 0. So this is unity and I am multiplying the metric tensor with unity. So I should get the metric tensor itself, right? Because I am multiplying it with unity, but I'll not get the same metric tensor. I'll get g here, mu alpha and alpha are summed over, so I'll get g nu mu, right? And similarly here I will get, if I multiply these two, I will get r mu nu. or r nu mu, okay, minus 1 by 2, and this r will be there as it is equal to 0. And this quantity in the bracket, I call it as the Einstein's tensor or the Einstein tensor. Therefore, I can write G mu nu is equal to 0. Okay. So this is the Einstein tensor. Einstein tensor G mu nu is equal to r mu nu minus 1 by 2 G mu nu r. This is known as the Einstein tensor. So this is the tensor that I am going to equate with the energy momentum tensor. Okay, so Einstein tensor is a curvature tensor, form of curvature tensor, because it has the Ricci tensor and Ricci scalar. Okay, it has both Ricci tensor and Ricci scalar. So Einstein tensor is also a type of curvature tensor, but it has the properties similar to that of the energy momentum tensor, so that I can equate with the energy momentum tensor. So energy momentum tensor is the source for gravitation, and G mu nu, the Einstein tensor, represents the space-time or the geometry. So how do I equate geometry and the source? So that's how the Einstein field equation comes. So this is the geometry. Now geometry I have to equate with the source. Source is energy momentum tensor. This is geometry, and this is source of gravitation. So the equation that connects, so I can write a constant. So this is proportionality sign. So if I remove the proportionality sign, I can write a constant. Okay, so I'm removing the proportionality and I'm writing a constant times T mu nu. So the geometry is now being equated to the source of gravitation, which is the energy momentum tensor, and this equation is known as the Einstein field equation. Einstein field equation. G mu nu is equal to gamma times T mu nu is the Einstein field equation, which connects the geometry and the source. Geometry means the space-time, and source of gravitation, which is the energy momentum, distribution of energy and momentum in the space-time. Now this can be written in, Einstein tensor can be written in many ways. Okay, so one way is, this is, oh sorry, here I have made a mistake. G mu nu. Okay, so this is fully covariant form. You can write it in many ways. You can write in mixed form also. Mu nu is equal to r mu nu minus half mu nu r. This is a mixed form. Similarly, the fully covariant form and fully contravariant form also I can write. G mu nu is equal to r mu nu minus half G mu nu r. This is the fully covariant form. Now fully contravariant form also I can write. G mu nu is equal to r mu nu minus half G mu nu r. Okay, and I can equate this to gamma t. right? So in the first case it will be, here it will be mixed case, gamma t mu nu. Here it will be gamma t mu nu, right? Here it will be equal to gamma t mu nu, right? Yes. Now for time being, I'll take the mixed tensor. If I take the mixed form, then r mu nu minus half mu nu is equal to gamma t mu nu. So this is the Einstein field equation in the mixed form. So here if I put mu is equal to nu, I'm just contracting, okay? If I put mu is equal to nu, then I'll get r mu minus half del mu is equal to t mu. So this is r mu is r minus half. Now this is unity. So unity in 4 dimension, it will be 4, right? Remember, del 0 0 plus 1 1 plus 2 2 plus 3 3. So this will be 4. So unity in 4 dimension will be 4. So I am writing 4, then r is equal to gamma t mu will be t. So this will be r minus 2r is equal to gamma t, or I can write r is equal to minus gamma t. Okay, so here t is the trace of t mu, that is t0 0 plus t1 1 plus t2 2 plus t3 3. Okay, so t means the trace of the matrix t mu. So we have the equation r is equal to minus gamma t. So you can substitute it back to the Einstein field equation. So the Einstein field equation was r mu nu minus half g mu nu r is equal to gamma t mu nu. So here instead of r, I can write minus gamma t. So r mu nu minus half g mu nu minus gamma t is equal to gamma times t mu nu. Now I can rearrange and get r mu nu is equal to gamma, I'm taking outside, then t mu nu minus half g mu nu t. So here you can see the real connection. If t mu nu is equal to 0, that is, there is no distribution of energy or moment, or energy mass. There is no mass. If mass is equal to 0 and energy equal to 0, then t mu nu will be 0. Correspondingly, t will also be 0. If t mu nu is 0 and t is equal to 0, then you can see that the curvature is also 0, which means there is no curvature. So you can see that the energy momentum tensor and the curvature tensor, they are related. If there is no distribution of mass and energy, and then there is no curvature. Okay, so this is a very beautiful equation known as the Einstein field equation, which relates the curvature and the source of gravity. Okay, so maybe today's class we will stop here, and next class we will see what this gamma is. You have to find this gamma from applying the Newtonian approximation. Okay, so next class we will see what is gamma. We'll find that, substitute here. Okay, so here we stop.